Carlos N1CBM and Alex K1AOS are the pilots of the ECR Aeronautical Mobile 20-meter net. This exciting project connects aviation and ham radio operators in a whole new way. The first flight happened on Friday, January 10th, going from Teterboro, New Jersey, TB, to Gainesville, Florida, GNV. Using 14.281 MHz, Carlos and Alex made 38 contacts during the flight. But they noticed a problem. Too many stations calling at once made it hard to log contacts while flying. To solve this, the team asked Vicky, KE8VKY, to help. She started logging contacts sent through the text line at 716-317-9050 before takeoff. You can monitor the periodically updated list at bit.ly/ECR logs and select Aeronautical. This made everything much smoother during the flight. On January 17th, the new plan was tested during a flight from Washington Dulles, D.C., IAD, to Naples, Florida, APF. When the plane reached 40,000 feet, Vicky uploaded a list of pre-flight check-ins to Carlos. He worked only from the list while Vicky logged everything from the ground. This system worked great. They doubled their contacts, even with a shorter flight. Thanks to Carlos, Alex, and Vicky for making the ECR Aeronautical Mobile 20-meter net a success. Their teamwork and quick thinking have created an amazing new way for hams to connect and to introduce different aspects of the hobby to newer hams. Stay updated. Flight times can change, so updates are posted on the ECR Facebook page. Follow us there to know when the next flights will happen. The team plans to fly twice a month with occasional pop-up nets. Visit us at Orlando Hamcation. From February 6th to the 8th, the ECR team will be at Orlando Hamcation. Visit our command center in the indoor flea market building at spaces W21 through W24 against a wall in the Swaps building. Come meet some of the team. We'll also bring a UHF repeater to help everyone stay connected during the event. Primary frequency, 444.200 MHz, plus 5 MHz offset, PL 88.5, encode and decode. Backup frequency, 444.150 MHz, plus 5 MHz offset, PL 88.5, encode and decode. Please program these frequencies into your HTs to make it easier to find and talk with each other. Note, this repeater is not connected to the ECR system.
ECR Aeronautical Mobile Net. The ECR would like to give a warm welcome to Alex, K1AOS, and Carlos, N1CBM, the pilots of the new Aeronautical Mobile Net. Join the Facebook chat under events at facebook.com/W2ECR to stay current. Flights may be delayed or canceled. This is the best way to stay current. Times, days, and frequencies vary and may change without notice. Orlando Hamcation, February 7th to 9th, 2025. This year, the ECR team will be at Hamcation in Orlando, located in the Swaps building. In ECR fashion, we're bringing our own UHF repeater. Details. Primary frequency 444.20 MHz, plus 5 offset, PL 88.5 encode decode. Backup frequency 444.150, plus 5 offset, PL 88.5 encode decode. Program your radios ahead of time to stay connected and enjoy the event to its fullest. Ask an Elmer recurring Zoom room event. Ask an Elmer, be an Elmer, or just come and listen, where your questions and your knowledge are an asset to amateur radio. Every first and third Thursday of the month at 8 p.m. To enter the Zoom room, go to bit.ly/ECR daily.
The Antenna Farm by KC6UFM, Part 28, Reactance and Impedance. Hello, ECR family, and welcome to the Antenna Farm. This is your friendly antenna farmer, Charles, KC6UFM. As always, with the Antenna Farm topics, I welcome any and all feedback from you, the reader. I am almost always monitoring the East Coast Reflector, and my email is on my QRZ page. I am also on the ECR for almost every Tuesday night TechNet, so this would be a great place to ask questions too. Feel free to reach out to me with any comments or questions. But there's a new, and in my opinion, great place to ask questions about the Antenna Farm or antenna systems in general. Join me along with other Elmers in the East Coast Reflector Zoom room on the first and third Thursdays of each month at 8 p.m. Eastern for the Ask an Elmer, Be an Elmer event. This is the chance for all hams, especially those new to the hobby, to ask questions that may be too involved to get answers from the TechNet. I look forward to you joining us and asking your questions. In this article, we're going to take a little side trip into a part of the antenna farm that I like to think of as the herb garden. Here we'll find topics that, while not actually about antennas in a specific way, are nonetheless important to know about. The herb garden tends to be a little more technical and theoretical than just a simple how-to for building an antenna, but we'll try to keep things as simple as possible, while still giving you the knowledge needed to move forward with our overall goal of building, using, and understanding antennas. I get a good number of emails asking about impedance and what it is, and more importantly, what it means in terms of antennas. And so, on this trip to the herb garden, we're going to have a look at impedance and reactance. Please note that as with all antenna farm articles, the goal is not to turn you into an electronics expert or a physicist. The goal is to give you the information and skills needed to understand, build, and use antennas. To this end, there are situations when some intricacies of the hard science are simplified, sometimes overly so, in favor of clarity and practicality. Those really interested in knowing the details of how this all works should dig a little deeper. Ohm's Law. To put the entire reactance and impedance issue into context, we need to do a short review of Ohm's Law. Ohm's Law is a very simple set of equations that show the connections between four basic values found in electric circuits. The values are defined as voltage, usually represented by the variable E, short for electromotive force, is the pressure that moves electricity through the conductors, measured in volts. Current, usually represented by the variable I, from the French phrase intensité du courant, which means current intensity, is the volume of electricity passing through the conductors, measured in amps. Resistance, usually represented by the variable R, for resistance, of course, is the opposition to the flow of current in a conductor, measured in ohms. Power, usually represented by the variable P, or sometimes W, is the amount of work that is generated by the electricity moving through the conductors, measured in watts. Some of you, just by reading the above, will have a hint that there is a clear mathematical relationship between the four values, but we're not going to dive down the rabbit hole of just how and why that is. All you really need to know is that there is a relationship and how to use that to your advantage. The chart below shows the possible equations for using Ohm's Law. In short, if you know any two values, you can easily calculate the other two. To use the chart above, just find the two values that you know on the outer ring, and the inner ring will show you what you can calculate using those two values. For example, if you know the value for resistance, R, and power, P, you can calculate the value of the current by taking the square root of P over R. Here's a tip. If you're good transposing equations, simply remember the two equations from the chart of E equals I times R and P equals I times E, and transpose as needed to get all of the other equations. For an example, let's assume that we measure a resistance, R, of 1 ohm and a voltage of 1 volt. We can calculate that the circuit will have 1 amp of current. I equals E over R, I equals 1 over 1, I equals 1, and a power of 1 watt. P equals I times E. P equals 1 times 1. P equals 1. Ohm's law applies to both DC, direct current, and AC, alternating current systems. Sort of at higher frequencies of AC, such as the RF ranges that we hams use, there is an effect that begins to take hold, impacting the resistance of a circuit. We call this effect reactance. Reactance. Strictly speaking, the total opposition to current flow is made up of two components. Resistance, as above, the opposition to the flow of current, and is usually made up mostly of the resistance of the conductor itself. For example, Number 12, a WG copper wire has a resistance of about 1.6 ohms per 1,000 feet of wire. This resistive component is independent of the frequency of the applied voltage. Reactance. This is the opposition to the flow of current presented by non-resistive components like capacitors and inductors in a circuit. Reactance is usually represented by the variable X and is also expressed as ohms. There are two things to keep in mind. 1. The value of X can be either positive or negative. And 2. The value of X varies with the applied frequency. In DC or very low frequency circuits, we usually ignore the reactive component, and this is, more often than not, a safe assumption. At RF, however, we must consider reactance, and you'll see why in a few moments. Impedance. In the real world, we have a value called impedance, the total opposition to current flow in a system, usually represented by Z and measured in ohms. Again, impedance is simply the sum of the resistance and reactance, so Z equals R plus X. Remember that while R will always be a positive number, X can be either positive or negative. In other words, if you have a circuit where R equals 10 ohms and X equals minus 5 ohms, the impedance will be 5 ohms. Reactance and frequency. There are two types of electronic components that will create reactance, and both are impacted by the applied frequency. We're going to look at these components separately. Capacitors. A capacitor, condenser for you old-timers, is nothing more than two conductors separated by some insulator. A capacitor works by storing an electric field between the two conductors, and then releasing that stored energy back into the circuit. The exact form of the conductors and insulator doesn't matter. You can make a crude capacitor with two coins having a sheet of paper between them. A few common symbols for a capacitor are in the schematic image. The schematic symbols for capacitors show the two conductors separated by an insulator. Just based on the fact that a capacitor is two conductors that are insulated from each other, it's obvious that at DC, frequency of 0 Hz, a capacitor is an open circuit with a reactance and impedance of infinity. Think of a capacitor at DC as an open switch, but only at 0 Hz. As the applied frequency increases, the reactance of a given capacitor decreases. If, for example, we use a 1,000 picofarad capacitor at DC, the reactance is infinity, but at 60 Hz, US mains frequency, the reactance becomes 2,652,582 ohms. At 28 MHz, the ham 10-meter band, the reactance is only 5.684 ohms. The formula for calculating capacitive reactance is XC equals 1 over 2 times pi times F times C, where XC equals capacitive reactance, pi equals 3.1416, F equals frequency in hertz, C equals capacitance in farads. When used in equations by convention, we consider capacitive reactance to be a negative number. Inductors. An inductor is nothing more than a conductor made into a coil. An inductor works by storing the magnetic field part of the applied signal and then releasing that stored energy back into the circuit. A few common symbols for an inductor are image of inductor schematic. Again, similar to capacitors, the schematic symbols show that the inductor is a simple coil of wire. Based on the fact that an inductor is coil of wire, it again is obvious that at DC or very low frequencies, an inductor will have very low reactance, and its impedance is mostly the resistance of the wire. Think of an inductor as a dead short, but only at DC. As the applied frequency increases, the reactance of a given inductor also increases. If, for example, we use a 1000 mH inductor, at DC, the reactance is 0 ohms, but at 60 Hz, US mains frequency, the reactance becomes 377 ohms. At 28 MHz, the ham 10M band, the reactance is 175,929,189 ohms. The The formula for calculating inductive reactance is XL equals 2 times pi times F times L, where XL equals inductive reactance, pi equals 3.1416, F equals frequency in hertz, L equals inductance in henries. When used in equations, by convention, we consider inductive reactance to be a positive number. It's worth mentioning that all components in an electronic circuit will display a certain amount of stray capacitive and inductive reactance, albeit typically very small. For example, the leads of a transistor will have some capacitance and some inductance. Depending on the circuit, this may be someplace between trivial and safe to ignore and critical enough to make the circuit not act as planned. Putting it all together, once we know the values of the resistive and reactive components, the overall impedance becomes nothing more than Z equals R plus XL plus XC. Remember, XC is a negative number, so if you have R equals 10 ohms, XC equals minus 10 ohms, and XL equals 20 ohms, the total impedance becomes Z equals 10 plus 20 plus minus 10. Z equals 20 ohms. But this impedance is inductive, and we need to keep that in mind. To help us do this, we will normally express the impedance above as Z equals 10 plus J 10 ohms. Bear with me for a moment. We need to get into the weeds of the herb garden. Mathematically, we treat reactance as an imaginary number because it makes the math easier in the long run. For reasons related to simplicity and avoiding confusion, when we're talking about reactance in electronics, we indicate an imaginary number by preceding it with the letter J. When dealing with antennas, you will see output from modeling software and antenna analyzers with an impedance shown something like Z equals 35 plus J 93, or Z equals 35 minus J 93. These numbers mean that the antenna has a non-reactive component of 35 ohms and a reactive component of 93 ohms, with the upper display meaning that the reactive component is inductive and the lower display having a capacitive reactance. The sign of the reactive component of the antenna is very important. Ideally, an antenna should be non-reactive, that is J0, and the resistive component should be equal to the feed line impedance and the output impedance of the transmitter. In the upper display above, Z equals 35 plus J93. If I can somehow add negative J93 to the antenna, the impedance will become Z equals 35 plus J0. In other words, if I can add 93 ohms of capacitive reactance, I eliminate the energy wasted in the antenna through the reactive component. Why is this important? Because reactive loads do no work. Only the resistive component will make your signal better. And that is what we are looking for. When the impedance of the energy source, your transmitter, the feed line, your coax, and the load, your antenna, are all the same, you get maximum efficiency in the transfer of energy. Your transmitter and coax are purely resistive. That is, they have no reactive component. Your antenna is where the problem crops up. In general terms, an antenna that is too short for the desired frequency of operation will show an inductive component, and so can be lengthened electrically by adding capacitive reactance, like a capacity hat to the far end. Inversely, an antenna that is too long will appear with a capacitive component and can be shortened by the addition of some inductance, like a loading coil to the system. This ability to make the antenna appear longer or shorter electrically is also the way so-called antenna tuners work. These devices do not tune your antenna. They simply provide a match to your transmitter that is safe for the final amplifier. These matching networks add capacitance and inductance to the system to make the antenna appear non-reactive, with an impedance closer to the desired value, usually 50 ohms. The key thing to remember about impedance is that to get the best possible performance from your antenna system, the impedance of the transmitter, feed line, and antenna must be equal and, in almost all cases, should be non-reactive, that is, purely resistive. Often, in practical cases, you may not be able to accomplish this 100%, but you can get close with a little research and effort. By keeping in mind the ways that reactance and resistance interacts with frequency and how you can manipulate the total values, you will gain an understanding of how you are able to use these components to maximize the effectiveness of your overall antenna system to enable the best possible performance. Next time on the Antenna Farm, we're going to get back to actual antennas and take a look at horizontal loop designs that are easy to build and have surprisingly good performance. If you know of an antenna construction article on the web, please drop me a note with the pertinent information, and I will look at it for consideration as an article for the Antenna Farm. Take care in 73. Charles, KC6UFM.
Text line 716-317-9050. Text in your call sign to get on the log. The Morning Brew is a popular fast-paced net. It can be difficult for new hams, digital, or EchoLink users to get through the pileups. The text line helps to ease the pileups and get more hams on the air. No in and outs accepted. No earlier than 30 minutes before the net. Connect to ECR. For a printable list of ways to connect, go to bit.ly/ECRConnect. For a list of known full-time repeaters, go to eastcoastreflector.com and scroll down to the map.
RF Attenuator Construction Project by Randy, W2RBC. Uses for an RF attenuator. An RF radio frequency attenuator is a device used in RF circuits to reduce the power level of a signal without significantly distorting its waveform. Attenuators are commonly used in various applications to manage signal levels, protect sensitive equipment, improve radio direction finding accuracy, and to assist finding sources of RF radio interference. Signal level adjustment. In RF systems, it is often necessary to adjust the signal level to match the input requirements of different components, such as an amplifier or receiver. An RF attenuator can reduce the signal power to a suitable level. Protecting sensitive equipment. High-power RF signals can damage sensitive components in test equipment, such as VNAs and spectrum analyzers. Attenuators are used to reduce the power to a safe level before it reaches these devices. Radio direction finding. When a handheld receiver and directional antenna is used to locate a source of RF signals, a signal attenuator is needed to limit the received signal level. As you get closer to the signal source, the signal becomes stronger. Without an attenuator, the signal can become so strong that it overloads the receiver, causing distortion, inaccurate signal strength readings, and making it difficult to determine the direction to the signal. While trying to determine the direction to a signal source, the attenuator should be used to reduce the received signal strength to approximately 1/2 of your S-meter scale. This makes it easier to see a rise or fall in signal level as the antenna is rotated. Minimizing interference. In environments with a lot of RF noise or interference, using an attenuator can help by lowering the desired signal level to just above the noise floor. This makes the detection of the signal easier by eliminating signals below the level of the desired signal. Assist finding sources of radio interference. This is similar to radio direction finding, but incorporates the use of computer software to plot the signal levels of the interference signal as the receiver is moved. The use of an RF attenuator, similar to the one in this document, is described in the W4DD presentation of RFI interference. The presentation was made on September 8, 2022, using the ECR Zoom room. The presentation can be viewed at youtube.com/@EastCoastReflector. Circuit description. This design utilizes a string of pi attenuator stages. Each stage is independent of the others in the attenuator string. By using the correct resistance values for the parallel and series resistors, the input and output impedance of each stage is equal to approximately 50 ohms. This allows adding additional stages without affecting the operation of the other stages in the string. For example, if you need to add an additional 20 decibels of attenuation, just duplicate stage 4 of the schematic S4, R10, R11, and R12 between the original stage 4 and connector J2. RF attenuator operation. When an input signal is connected to J1, switch S1 can be set to bypass the first pi attenuator stage, which connects the signal directly to the second stage. If the switch connects the signal through the first stage, the resistor values for that stage determines the insertion loss. This attenuated signal is then connected to the second stage. This process is repeated for all stages. To calculate the total attenuation, Add the attenuation of each stage that is connected. The sum is the total attenuation. Construction details. This is a very simple build that can be customized to fit your needs. Almost any sealed metal box can be used. The input and output connectors can be UHF-type bulkhead connectors, but BNC bulkhead connectors will also work. Almost any type of insulated wire is satisfactory. The bill of materials specifies low inductance resistors for the assembly. Finding through whole low inductance resistors is becoming more difficult as time goes by. The preferred resistors would have been carbon composition resistors like the obsolete RCR series of resistors. The next best would be low inductance metal film resistors designed for high frequency use. Since these are difficult to find, and often several dollars per resistor, I called out generic 5% metal film resistors on the bill of materials. Each of the resistance values called out are standard 5% values. Image bill of materials. Construction options. Because this design is intended to be used as an uncalibrated device, the 5% metal film resistors are sufficient for use. If a slightly more accurate unit is desired, consider using low inductance 1% resistors. If 1% resistors are used, they must be low inductance. If they are not, the accuracy attained will not be much better than what is obtained using 5% resistors. Notes: two resistance values are shown in table number 1. The 1% values produce an input-output impedance value of 50 plus or minus 0.1 ohms. The 5% resistor values produce the following input-output impedance values. 3 decibel setting, negative 49.2 ohms, 1/2 power. 6 decibel setting, negative 49.9 ohms, 1/4 power. 10 decibel setting, negative 49.5 ohms, 1/10 power. 20 decibel setting, negative 50.5 ohms, 1/100 power. Substitute the 1% precision resistor values if more accurate input-output impedance and decibel insertion loss are required. The use of low-inductance carbon composition resistors are preferred. Low-inductance metal film resistors may be used. This is a receive-only RF attenuator. Do not use when transmitting.
Consider being a contributor. Send in your article, project write-up, pictures, story, comments, and suggestions to editor.ecr@gmail.com. You don't have to be a good writer if you have a good story. Everything will be polished and sent to you for review before it's published. Okay. Audio feed. There's a new audio feed on the website. We still have the old one too, but now we have one live feed and one feed that has a 2.5-minute delay. Need an audio check? To hear what your audio sounds like, load up Listen Live on the website, pick up your radio, give your call sign, and say, "This is a test. No response needed." Still stumped? Come to our Zoom room for advice at bit.ly/ECR daily.
SM0VPO Bespoke Ceramic Capacitors. Introduction. I was made redundant as from the 31st of December 2023, so now, at 72 years, I am retired. I'm starting to play catch-up, not catch-up, with some of the projects I never had time for. In 2023, I did work on projects that were not documented. One of them is an FM transmitter that required a few oddball capacitors, for example, 3.647 picofarads. It needs very special capacitor values because it is an elliptic filter, having responses at specific frequencies. This makes it extremely difficult to get the exact values needed. This is the circuit I am building. Image caption. The filter I am building with oddball capacitor values. I made the PCB to accept 2 capacitors for each value so that you can insert a combination of 2 using standard values. 1 PF plus 2.7 picofarads equals 3.7 picofarads, which is close enough to 3.647 picofarads. But would it not be nice if you could adjust the value of a standard NPO ceramic capacitor? Well, you can. Read on. Method. I did not have any standard values lower than 10 picofarads, so I thought about it. Why not cut the capacitor in half? Take a look at a typical ceramic capacitor. From the side, it is simply a disc with 2 wires attached and encapsulated to protect it from the elements and dirty constructor's fingers. From above, it can look something like this. Typical ceramic capacitor construction: left, side view, right, top view. Take a nice sharp pair of wire cutters, cut off the top half. If you do this, then a 10 PF will become about 5 PF. If you want a small decrease, then clip off less than 50%. If you want an exact value, then you can take a cheap lady's nail file. That is not a cheap lady's file, but a lady's cheap nail file. Sorry. Now you can file a bit more off to get to the exact value you want. Remember that you can always cut a bit more off, but you cannot put it back, so start with the capacitors having the highest values. If you file off a bit too much and the value is lower than you want, then continue filing to get the next value on your list. Cheap nail files have something like 4 or 6 different grades of roughness, from ripping fingernails out to about as soft and effective as toilet paper. These are perfect for this job. Calibration. Calibrating the capacitor is far easier than you would think. I used a 10K resistor in series with a tuned circuit. The coil I used was 3 turns of 0.8 mm diameter enameled copper wire, close wound on a 6 mm drill bit. The coil will spring open about 0.5 mm when you stop winding. Keep the leads as short as possible, typically 5 mm. This has an inductance of 0.099 microhenries. Using the basic formula, 0.099 microhenries and 3.647 picofarads will have a resonant frequency of 264.8 MHz. The 10K resistor is to be sure that you only measure the tuned circuit response without any other form of loading. Test setup for adjusting capacitors. If you do not have a spectrum analyzer with a tracking generator, then you can use a 1-turn loop on the coil of a grid dip oscillator, GDO, and view the RF on an oscilloscope. I tested this with a 100 MHz scope. The oscilloscope frequency response does not matter at all. You do not need it to be calibrated. You only need to see the sharp dip when the generator passes through resonance. If necessary, then you can use a larger coil to get a lower test frequency. Basic frequency formula. Frequency F equals 1 over 2 times pi times the square root of LC. Typical display on the analyzer. The dip is still low in frequency, so a little gentle filing is still needed. When the capacitor is mounted on the PCB, the wire leads clipped off will reduce the capacitance a bit. Leaving the frequency just a tad low is good. When you check the final filter, you can always trim the response if it is needed. Remember that the formula for frequency uses the square root of capacitance, which means the effects of stray capacitances are smaller than the capacitance changes. If the capacitance error is 10%, then the resultant frequency error will be only 3%. Finished capacitor. When you have finished, then the capacitor will look like this. When the capacitor has been finally trimmed in circuit, then a small dab of cheap lady's nail varnish will seal it. I did it again. I mean cheap lady's varnish, but not the varnish from a cheap lady, sorry. The elliptic filter section of the finished transmitter looks like this. Note that the coils have been trimmed using the same test circuit. When the capacitor has been finally trimmed in circuit, then a small dab of cheap lady's nail varnish will seal it. I did it again. I mean cheap lady's varnish, but not the varnish from a cheap lady. The elliptic filter section of the finished transmitter looks like this. Note that the coils have been trimmed using the same test circuit. It is worth noting that I chose one inductor as a reference, L1 99.05 picohenries, and adjusted all the capacitors using this as a reference. The winding details I took from my coil winding data. I then took one adjusted capacitor and used that as a reference for adjusting the inductors. If the coil has an error of, say 3%, then all components will have the same error, but the proportions of the values will be as close as you calibrate. That is to say that the values are all relative, and so any error will be negated. In the above picture, you can see that the coils are all close, 3 turns, but I adjusted the spacing a little to get them exact. I did select a 10 picofarads when I wound L1, just to be 100% sure that the calculations were correct. When adjusting the components, you need to have access to the 2 relevant calculators. L1, reference inductor, 99.05 picohenries in the test circuit, with 33.102 picofarads, will give a dip on the analyzer at 87.895 34.6390682 Hz, 87.8953 MHz. Single layer coil. Finally, I hope that this project has given you some food for thought. You can always email me at harry.lithal@sm0vpo.com. You can even use oeieio@hotmail.com or hotmail@sm0vpo. As they are both valid email accounts for me, although I would prefer that you visit my message board if you have any questions about this or any other project. I always look forward to receiving feedback, positive or negative. Very best regards from Harry Lithell.
Swap and Shop. The Swap and Shop is completely free to list your items. Send your list in soon to make the next Tuesday night TechNet and Reflector magazine. Send your information to ve3bz@rogers.com. Visit the ECR Shop at eastcoastreflector.com. Most items are 15 to 30% off. Get t-shirts with your call sign starting at $17.68, mugs for $11.20, phone cases from $18.16, and hoodies from $38 up to 3X.
Celebrity Call Sign by Joe, KB2TFB. Larry Junestrom, WN4LKF. Bassist for Lynyrd Skynyrd and 38 Special. Larry was born on June 22, 1949 in Pittsburgh, Pennsylvania, and grew up in Jacksonville, Florida. In the 5th and 6th grade, he was in the school band as a saxophonist. Although he received an electric guitar and amp as a Christmas present, he found himself more drawn to the bass lines of songs, and modified his guitar with some balsa wood, effectively making a homebrew bass. Larry was first licensed at the age of 13 as WN4LKF and shortly thereafter as WA4LKF. In other words, the second letter of his call sign changed to Alpha. He only kept at the hobby a few years though, because he was more destined for a life in professional music. You see, in 1964, he was one of the founding members of the band My Backyard. If that doesn't quite ring a bell, maybe you're more familiar with the name after the change in 1969 to Lynyrd Skynyrd. After that, in 1977, he left Skynyrd to join another quite successful band, 38 Special. In early 1990, a local newspaper article about ham radio rekindled Larry's interest, and he proceeded to go from novice class to extra over a 10-month period. He was issued the advanced class call sign, KN4UB, but he thought of it as known nationwide for ultimate bass. He decided to stick with that call for 7 years. When he noticed K4EB was available, he decided to go for that vanity call. To him, this stood for known for excellent bass. This celebrity call sign belongs to Larry Junestrom, bassist for Lynyrd Skynyrd and 38 Special. He had to retire in 2014 from 38 Special due to arthritis. You can read more details about his ham accomplishments on the QRZ page for K4EB. Unfortunately to report though, he became a silent key on October 5, 2019 at the age of 70. Any text from Wikipedia is subject to the Creative Commons Attribution Sharealike 4.0 license. The primary source for this celebrity call sign is QRZ, with some help from swampland.com and the English language Wikipedia.
Comic page.
Daddy just wants to bond with you. Don't you want to be a ham?
Can I just pay a dowry? It would be so much cheaper.
Merry dang Christmas. Now they all want to be like Rudolph. Tell the elves I'm going to need ferrite rings for the reindeer.
Jeff? You know the new scanner you bought? The one that gets the police and army and everything? Are you sure they can't work out if you're listening illegally?
Riddle me this, fellow ham. I'm a contest of voices, a global affair. Operators compete from here to there. Logging contacts, day and night. What am I? A ham's delight. Can you figure it out? The answer is Field Day.
All times are Eastern. The following events are on the Reflector. For connection information, go to bit.ly/ECRConnect. Check out the Morning Brew Net on your way to work. Weekdays from 7 to 9 a.m. It can be pretty fast-paced. If you like a slower, more rag-chew net, stick around on Fridays after the morning brew for the second cup at 9 a.m. Have a technical question? Stop by the ECR TechNet Tuesday nights at 8 p.m. to ask question or offer your advice. On Sundays, listen to Amateur Radio Newsline at 1 p.m. and again on Wednesdays at 10 p.m. We've also got HF nets. On Thursdays at 10 a.m., join the 20-meter net on 14.317, and on Saturday mornings, go to 7.245 at 9 a.m. For the following events, join the ECR Zoom room by going to bit.ly/ECR daily. Every day at 3:30 p.m., stop by for advice or just casual conversation. Check out the Ask an Elmer Zoom room for people to seek information and to offer help to hams with the utmost respect, or you can just stop by and listen. On the second and fourth Thursdays is the ECR Think Tank, where users help to come up with and execute new ideas to help the ECR moving forward. Reflector Etiquette. We don't have strict rules, but we do have guidelines that help make the best experience for everyone. This is a very large system, with hundreds of connections at any given time. All of these repeaters and nodes can take a few short seconds to receive your audio, so key up and wait 2 seconds before you start to talk. Some repeaters have longer delays than others. Please feel free to use the Listen Live audio on the eastcoastreflector.com website to hear if you're cutting yourself off. Keep your transmissions to less than 3 minutes. You won't only time out your repeater, but many others. Limit QSOs to 15 minutes. With hundreds of people, everyone needs a chance to talk. For the same reason, leave 3 seconds breaks between transmissions. If you don't leave a break, the system doesn't know you're not still the last person, and the time will compound and time out the system as well. Politics and religion are very important, and we respect your opinion and beliefs, but this isn't the place for its discussion. Politics and religion make people too emotional to maintain a family-friendly environment. Only use the break or break in an emergency. Listen before you speak. Don't break into a net or QSO for a radio check. You only need to ID every 10 minutes. People tend to get carried away and say it after every transmission, even if they're transmitting every minute. A lot of hams don't appreciate CB terms like 10-4, good buddy, home 20, personal, or Roger. The reflector is over the internet. Everyone hears the same audio. There's rarely a need for the use of phonetics. Make sure your email on QRZ is public. This is the way people can contact you, especially if there is an issue with your node or repeater that you may not be aware of. Lastly, fix poor audio. If you need help with your audio, we'd love to help. Stop by the ECR Zoom room at bit.ly/ECR daily. Website. Check out the ECR website at eastcoastreflector.com. You can view the monitor to see who's talking with the last heard feature. Go to the contact menu and submit suggestions for TechNet or Morning Brew questions, ask general questions you need help with, or report issues. Other features include a map of known full-time repeaters, joininggroups.io, a link to the ECR Zoom room, links to each net and their log sheet, the ECR Shop, and, of course, the Reflector magazine at eastcoastreflector.com/magazine. Facilitators. In no particular order, WB2JPQ Dick, the founding father, or should I say godfather of the East Coast Reflector. KB3 SNM Bob. He's been around since the beginning of the Reflector. He's known as the junkyard dog. He's right on top of any issues to help ensure that people don't get out of line and ensure family-friendly airwaves. KB5 GLC Keenan, a vital part of the ECR and one of its data centers, he's a much appreciated part of the team. K4FXC David, HamVoIP himself, and an essential part of the ECR as its data center. KE7K Kevin, with over 14,000 users, Kevin maintains our database, sets up Amateur Radio Newsline for you to hear on the ECR, announcements, and many other things including the TechNet. KO4FRR Joe. Joe is the man that makes the text line possible. He's also the webmaster and computer guy. W2RBC Randy, he one of the magazine authors, webpage, groups.io, runs the ECR think tank and various other things including the HF nets. K2CMT Mike, the infamous Morning Brew net controller. Mike has the Kentucky ability to turn a 4-syllable word and turn it into one. KD2VNU Dan. Derby Dan is the Youth Net director. You'll find him behind the scenes during the Youth Net helping the kids to make the magic happen. KY4ATF, Rome. Rome is the guy that made our website the best in the industry. Don't believe me? Check it out at eastcoastreflector.com. W2KJV Tony, our YouTube man, he takes the pictures you send in and puts them into a video for everyone to see. K8BAC Al. Al is a net controller of the Morning Brew and on our 40-meter net. He's a very welcomed recent addition to the team. N2BH Bill. Bill is a net controller for the Morning Brew, and you can usually find him helping at ECR events and ham fests. W2PUT Dan. Dan is both one of the newest and oldest facilitators on the ECR. He helped to start the ECR and has recently had time to return and help out on the Ask an Elmer, as well as write a few articles for the magazine. KE8VKY Vicky. Vicky is the editor of the magazine, made and maintains the logs with the help of KE7K, and can usually be found on the net's logging. VE3BZ. Kevin, Canadian Kevin. He's our nighttime security guard. He takes care of the system while the rest of us sleep. You'll also find him once in a while logging for Alex, W7FTM on the Trivia Net. Also, we'd like to mention some of our other contributors. W2BLT, Scott, the Morning Brew Net, Coordinator and Net Controller, KE0GKF, Jeff, Morning Brew Net Controller, W7FTM, Alex, Trivia Net Originator and Net Controller, KO4QMM, Roger, our 20-meter net controller, and occasionally the Tech Net. And our youth net controllers, KD2YHZ Luca, KD2YFO Aiden, and KG4BUT Grayson.
Please pray for Cindy, wife of Charles, KC6UFM. Please pray for KC9TW, Jeff for kicking cancer's ass. Please pray for KC9TWXYL, Jeff's wife, for a quick recovery. Please pray for Nick LeBlanc, brother of Joe KO4FRR. Please pray for Deborah Enos, wife of Mike KB2UDB. Please pray for K1MCO Javier. You're all in our prayers. Silent Keys. AF6GD Charles. LA8W George. W8GUC Ruben. K2NXY Thomas. K2ZS Gordon. W5CJ Barry. W9XTZ David.
You should know. The East Coast Reflector and its Reflector magazine is all volunteer run. We charge nothing to use the system. We charge nothing to subscribe to the magazine. The system has hundreds of users connected at any given time. We incur a lot of expenses to maintain such a large system. If you use the system or enjoy the magazine, please consider helping by contributing to the system by going to eastcoastreflector.com and click on Donate. Your contribution is greatly appreciated. Thank you for listening to the Reflector magazine. If you'd like to subscribe, go to bit.ly/ECR subscribe and enter your email.
Disclaimer. The content, opinions, and views expressed in this magazine are those of the authors and contributors and do not necessarily reflect the opinions or views of the publisher, editorial team, or affiliated organizations. All articles, images, and information provided are for informational and entertainment purposes only and should not be considered as professional advice. The publisher assumes no responsibility for errors or omissions in the content provided. Readers are encouraged to verify all information independently. The use of trademarks, logos, and brand names does not imply endorsement. Reproduction or redistribution of any content in this magazine in whole or in part, without prior written consent from the publisher, is strictly prohibited. For inquiries or permissions, please contact Vicky K8VKY at 8VKY@gmail.com.